Uh, am I audible?
Yes, sir.
Okay. Yeah. So good evening, everyone. Today we'll still talk about classification, but a bit more about two more classification algorithms. What are the two classification algorithms that we saw before?
So gain and logistic regression.
Hmm. Okay. So yeah, care and registry regression. Today we'll look at naive-based classifier and support definitions. Okay. Um, Summary on KNN. It's just you have a bunch of points belonging to different classes. You have a new point coming in that you want to classify. You look at the k nearest neighbors. If it's classification, you take the majority class. If it's regression, you just take the mean value, okay? Just average. If k is 3, you take the three nearest points. If two are class B, one is class A, you assign this point to be in class B. Okay, this KNN. Uh, Logistic regression, again, it's between, it's just linear regression with the sigmoid, this activation at the end. What it will do is it will give you a probability between 0 and 1. If the output value is greater than 0.5, you say it's class 1. If it's below 0.5, you say it's class 0. That's it. Okay. Simple. Uh, we also looked at evaluation metrics. For regression, it's R square, coefficient of determination, mean square error. For classification, we saw it as FN score, accuracy, ROC, AOC, precision, and recall. All these things we were able to calculate in the tutorial also. Okay. And we also saw a bit about this confusion matrix, how to calculate accuracy, efficient recall from this accuracy matrix. Ultimately, we want the model to have higher number of true negatives and true positives. Okay. And also we saw a bit about splitting strategies. Can anyone explain what's the splitting strategy that we saw? There's a specific name for it. The default one is you just do train to split once, and do train your model on the train data, then test run history. What about the other ones that we saw? It was called cross validation, no?
Yes, sir.
So yeah, cross validation. You have multiple splits, let's say 100 data points. You have 10 different splits, each containing 10 data points. You take the first 10, keep the other one for validation. Then you take the second set of 10 batches. Then you keep something else as validation set. So this goes for 10 times. That is what is called 10-fold cross validation. That we'll see in the next tutorial that we have. Okay, but for now, this is all we learned in the last class. Any doubts in the previous classes?
No, sir.
No, sir.
Okay. So we'll start with the naive-based classifier. Okay, it is what I would call a probabilistic classifier, and it is based on this Bayes theorem. Okay, if you learned a bit of probability in high school, uh, you might know about this Bayes theorem. Uh, what it essentially says is probability of y given this event x happens. Okay, it is probability of y times probability of x given y happened, and probability of x. Okay, this is more this is more like a conditional probability that, let's say, okay, you are tossing five different you are tossing a coin randomly like five different times. Okay, what is the probability that the sixth time when you toss a coin is also a head? Okay, for that, this should be like previous time what all events happened, you combine, and the next coin toss that you do is sort of like dependent on the previous sequence of events. Okay, that's what Bayes theorem essentially says. Okay, or it can be like, what's the probability of you having a cold given that this test is positive? Okay, that means that even though this test is positive, doesn't necessarily mean that you have a cold. So it can be interpreted in these two ways, because the test might also be wrong at times. Okay, not everything is 100% accurate. Okay? You have to take all these into consideration. And again, so there is a very popular example. You have an individual, okay, who goes to a hospital to take a test and determine if she has diabetes. Okay, the overall probability of having diabetes is 5%. Okay, this is the prior probability. Okay, that is P of X. So if she obtains a positive result, okay, the prior probability is sort of like updated. Okay, and this becomes the posterior probability. That is this one. Okay, and this is how you calculate. Okay, so how an I-based classifier works that you calculate the prior probability given the class labels. That is the P of y. Okay, P of y. This you can calculate. Let's say uh, you have let's say the total number of data points is 100. Among that, 90 of them belong to class 1. Okay, what's the prior probability for class 1? Can anyone tell me? You have 100 data points, 90 are class 1. Prior probability for class 1.
So 9/10.
So it's 0.9. Yeah, correct. Okay. Then what you do is you find the likelihood. Likelihood is essentially this term. Okay. P of X you don't need to worry about right now, but this is prior, this is posterior, this is uh, likelihood. Okay. Put these values in the formula and calculate the posterior probability. Okay, and you do it for class 1 and class 0 and see whichever has higher probability, the input belongs to that class. Okay, this is how you do it. And let me show a small example. Okay, this, so given the weather conditions, okay, you have to sort of predict whether a group of people will play cricket or not. Okay, sometimes when it's sunny, they'll play. Sometimes when it's rainy, they won't play. Or even when it rains, they might play. So this is different, dependent on different groups. Okay. So what you first do is calculate something called the frequency table. Okay, you have the weather. Okay, weather here, and let's say for overcast, how many no's are there? Okay, or how many yeses are there? This is essentially your frequency. For overcast, there's 0 no's and 4 yeses. Okay. Similarly, for sunny, rainy, and total number of no's and yes. Okay. So what's the prior probability for this data set? Prior for yes. What is that?
9/14.
Yes, that is correct. Okay. It's 9 by 14. That's what you essentially have here. Okay. And you can calculate the likelihood. Okay. Likelihood is you can do it across this table. Okay. In this case, what is the likelihood? Probability of, let's say, overcast, given that you're already playing. Okay. So this is how it works. Probability of overcast, given that you say yes, that is 4 by 14. Okay. And same thing, probability that you say weather is sunny and rainy. So you should essentially like sum up these two terms and divide by the total number of terms. Okay, you have all these. And let's calculate the posterior probability. You don't worry about P of X for now. You can leave it as such. Okay, because essentially you want to compare the same terms. You're not comparing different terms, so you don't need to like sort of marginalize the probability that you have. Whichever is higher, that is your class. Okay. So this is let's say you want to predict the probability of yes, given that this is the weather condition is overcast. Y is always your label. Okay, you have to remember that Y is always your label, and X is the weather term that you have. So what you do? So this is the likelihood is 4 by 14. Okay, and this prior probability that you have. Okay, that is essentially like 9 by 14. So the posterior probability will essentially be like 4 by 9. Okay. Posterior, so okay, when you compare the overcast weather feature here, what you have is two probabilities. So now I'm asking you a question. When it's sunny, whether the group will be going to play cricket or not. Based on this table, you can tell me.
No, sir.
Why?
So because the probability of overcast is higher than the sun.
No, 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 no. I shouldn't look at it that way. When it's sunny, whether they'll play or not. So you have to compare these two quantities. Overcast, you don't worry about that. Okay. When you look at one specific feature, you forget about the rest of the features. That is what I call the naive base. That's why it's called naive base. Naive base meaning you don't see any interaction between features. That's one of the disadvantages of this classifier. You won't be able to capture interactions and all. So when I say it's sunny, you don't worry about overcast or rainy. You just see this row. Based on this row, tell me whether they'll play or not. Just compare these two
No,
probabilities
sir.
and tell me why.
The same because of yes and no probability is higher, sir. No probability is more than yes
So
probability.
yeah, no probability is higher than yes probability. Okay, that's how you should compare. For rainy, what's the answer for rainy?
No, sir.
Yeah, because again, it's the same case. Okay, so this is how everything works. Okay, and it's very fast to predict the class of the test data point. Okay, and this is the best model to use when independence condition holds. So the independence condition meaning like, see, when it's overcast meaning cloudy. When it's cloudy, it might also say that it's going to rain. So there is this sort of dependence on these two features. But naive-based classifier doesn't look at all those dependencies. It's so they assume that the features are independent. Then also when you have categorical input variables, it's better to use naive-based. Some use cases for these are text classification recommended systems and so on. Okay. Any doubts in naive-based classifier? You just have to decide. I mean, once you calculate this likelihood table, it's 4 by 14, and then divide by the total number of yes or no. That's what you should do. That's it. Once you get this table, it's very easy to calculate the probability. Okay. Any doubts?
No, sir.
Okay. Uh, moving on to support vector machines. Okay. Uh, support vector machine is again, it can be used for both classification and recursion. The goal for support vector machines is to sort of create the best decision boundary, okay, that can segregate these two classes. Let's say this is class 1, this is class 2, okay, green and blue. I want to create a boundary between these two. How many lines I can draw between these two classes? Tell me. How many lines I can draw? How many number of lines I can draw between these two areas? Like this area, how many lines I can draw? How many number of lines? Think about it.
Sir, two.
Do you think only two is possible? Think. Actually, you can draw infinite number of lines. I can draw one like this, 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 like this. Like infinite number of lines you can draw at different angle. Okay. But Which one do you think is the best line to separate this area?
The line covers the points between the two classes.
Hmm, you mean like this or like this? See, it should be exactly in the middle, no, between these two. Because if some other point comes like this, I can say it's class blue. If some other point comes like this, I can say it's class blue. So it should be exactly in the middle, and these two distances should be equal. The line shouldn't be like here or here, giving more support to one class and so on. Okay, should be exactly in the middle. That's where this support vector machine comes into the picture. You see, this is one example, like two features. I can have multiple lines, like infinite number of lines. This is one line. I can draw one like this. I can draw one like this. I can draw one here. Infinite number of lines. But the very optimal line is exactly in the middle, okay, between this area. In this area, it should be exactly in the middle. This is what I call the optimal hyperplane. Okay, and this blue points that you see and this green point that you see, it is known as support vectors. Okay, let's say I put a point here, blue point. What will be the class for that? Is it going to be blue or green?
Blue, sir.
It should be blue. This, if it's this side, it's green. Okay, and the goal of SPM is to, this is the margin. Okay, the distance between these two lines is the margin. Goal of SPM is to maximize this margin. Okay, that's how it works. Let's say, and these are support vectors. The ones on this line, this red dotted line that you see, it's called the support vector. And this is your training set. What essentially matters is these endpoints. Endpoints only determine the position of this black line. Okay. Let's say I add a point here. I add a point here, like green point here and blue point here. Will my black color line, this line, the optimal hyperplane change or not? Think and tell. I put one blue here, one green here. Will my line change?
So I think no.
Why?
So because if the line, the margin is to be extended up to the height of the both points, it will cover the points. Thus,
Essentially, what these, if these one, two, these 3 points don't change, the line also won't change. Let's say I add one blue point here and one green point here. Will my line change? I put it one green point here, one blue point somewhere here. Will my line change? Just think and say. It will change because the support vector then becomes this point and this point. Okay. So you have to think about the end points. Okay. Then these two and this one will no longer be the support vector. The newly added point will become the support vector. If you add something outside this red dotted line, it won't affect it. If you put some training points inside, then it will affect. Okay. That's the conclusion from this diagram. Okay.
Okay, sir.
Okay. And so you have these models and everything. Let's look at the pipeline. Okay. The C values and K values that you saw in the previous tutorial, okay, those are actually called hyperparameters. And as you saw, changing different values also gave different accuracy values, right? Yes or no? Did the value of K give you different accuracies, different values?
Yes, sir. The C value can change. The accuracy will change, sir.
C value, K value, those are all called hyperparameters. Okay. So
Yes, sir.
how do you choose this hyperparameter is very crucial for your model performance. That is where you do this k-fold validation that you see here. Like you split it into 5 different parts, keep one for validation, keep the rest for training. Then essentially the gray ones you keep for training, the blue one will be your validation or testing data. You split it, and the final performance will be average of all these accuracy scores. Okay. And once this is done, you check and you do this for all different hyperparameters. Once you get the best performance, you choose that value for the hyperparameter that you have. Then you train a final model again on all training point. Then you get the final model which can be deployed in real life situations. Okay. Any doubts in this?
Sir, if K value is selected, then the output will optimize. We will stop us.
No, this K is different, that K is different. Here K-fold meaning how many splits. Like here K is 5 because there are 5 different splits of the same data set. Okay. That K is for K nearest neighbors.
Okay, sir.
Mm. Then this is K-fold cross validation. I mean, you will see all these in the tutorial. Okay. And this is an example of tuning. Like I have 3 different hyperparameters. Let's say it's K, C, and something for the same model. You try different combination of these 3, and you see how the performance also changes. Like let's say take this one. If you trace this line, like if I put 0.013 and 0.04, the accuracy is like 30% only. It's not good. But if I take 0.254 and let's say 0.01, like this line, if you trace, then that means the model has good. I mean, if you put these hyperparameters, you get the best possible accuracy. This word is essentially tuning. What we did is we manually changed different values and checked it, and you are only varying one hyperparameter. But if you look at two or three, you have to look at like combinations. The combination is really important. Any combination, you have to check and see what the accuracy is. That's how you typically work on like on any machine learning pipeline that is. Any doubts in this one?
Sir, suppose we take 4 parameters,
Mm-hmm.
we will cross check for all the parameters.
Yes, all the parameters.
Okay, sir.
That too, not like one by one. Okay, you should check.
Combinations.
Oh yeah, combinations. Yes. And same this hyperparameter tuning, it can be done with different methods. What we did was sort of grid search, like one hyperparameter, you tried all the combination. But let's say you have three hyperparameters, okay, each one having 10 different values. Totally, how many combinations you have to check? Three hyperparameters, each one having 10 values that you want to search. How many combinations in total will you have?
Sir, is n cube.
Hmm. You have to try 1,000 different models, and that is uh, a very long process. It's very costly to do. That's why there are like other methods like Bayesian optimization, GA, particle genetic algorithms, particle swarm optimization, and so on, so on. Okay. You don't need to worry about all these things for now. You just have to know the overall pipeline. Grid search is fine if you have like just three hyperparameters, each one having 5 values or something. But if you have a lot of hyperparameters, a lot of different values to check for, go with Bayesian optimization. Okay. That's what you need to see. Okay. So you start with one combination. You start with one combination, do cross validation, calculate the average accuracy, and say that okay, this combination has this much accuracy only. Okay, let me try a different combination. Then you go again, choose a different combination, you get different accuracy, and essentially you need to get this plot. Okay, that's how it works. And to sort of summarize, you saw two different new algorithms for classification, naive Bayes and SVMs. Naive Bayes is sort of the ideal classifier because it's very fast and but only works when the features are assumed to be independent. Okay. And SVM uses the maximal margin hyperplane. Okay. And ultimately, what you have to do at the end is tweak the hyperparameters for all these optimal results that you want. Okay. Uh, so I think we are done with naive base classifier and SVMs. Okay. I think, yeah, that's it for today's lecture. I mean, we will be discussing about decision trees. Okay, let me just check. Okay, I'll also finish decision trees. So, okay, this is another different model for classification. Okay, uh, what you essentially have in decision trees is a bunch of if-else statement. Okay, and it has a tree-like structure. This is what you call the root node, and these are your leaf nodes. Okay, it can be used for classification or regression problems. Same example we can take the weather example and whether they go to play or not. Okay. So first, at the very first node, root node, you ask, okay, what's the weather now? If it's sunny, overcast, or raining. If it's overcast, I'll definitely go to play. Okay? I'll definitely go play. That's one clear. If it's sunny, I'll also check the humidity. Okay, if it's sunny and humidity is also high, no, I don't want to play. Okay, it'll be too much hot and I'll be sweating a lot, so I don't want to play. Then if humidity is normal, okay, it's fine. It's manageable. I'll go play. But if it's rainy, you also check, okay, how strong is the wind? If it's very strong, it might be a cyclone. I don't want to play. And okay, wind is weak. Okay, I can go play. Playing the rain is okay. I like to play in the rain. Okay? Then I'll go play. This is how essentially a decision tree works. Okay? The problem here is you need to know which questions to ask at the right point. Okay. Here you know, okay, if it's sunny, I'll check for humidity. Here, if I check if it's rainy, I'll also check if it's windy or not. You know the questions to ask, but you could have also started with, okay, let me first check the humidity. If it's high, I'll definitely don't play. If it's normal, okay, then I'll check if it's sunny, overcast, rainy. I mean, this order of questions needs to be determined, and that's what you're going to look at now. Uh, Again, classification, regression, it can be used for both. If it's regression, it's sort of like average out the leaf nodes. If it's classification, it's just yes or no. So what though you have a root node, you need to ask a question. Then ultimately you keep asking questions. So that what you're left with is a bunch of yes and bunch of no's. Okay. Here you have to see that there is no yes, and here you have to see that there is no no's. It should be pure. Pure meaning, okay, once I ask this question, all yes should be in one side, all yes should be, no should be in the other side. That's what it means that the node is pure. And you also can choose like how many questions to ask and so on and so on. This is the root node, this is the interior node, this is the leaf node. Ultimately, leaf nodes needs to be pure. Like there should be only yes here or only no here. It should be like that. How do you construct decision trees? It's based on like again the homogeneity of the data. Homogeneity meaning, as I said, only yes or only no's. Okay. First, when you have two variables like humidity, uh, you want to determine whether to play tennis or not. Okay. If training shows that like 90% decided to play tennis and it's not humid, then you split that. Then again, when the not humid case is there, you split again and so on and so on. You just again, you don't need to worry about how to construct this decision tree as such. Some measures is to quantify this is called Gini index. Again, you don't need to worry about what a Gini index is and so on and so on. The advantage here is it's easy and fast. It can select very important. It can basically say that which question to ask first, which question to ask later, and so on. Okay. Disadvantages because, and one more thing you have to see is if you ask too many questions, the model will easily overfit. Okay, because if some other data point comes, you keep asking the same questions again and again. Like you ask a lot of questions, then you might be wrong. Okay? You need to limit the number of questions to ask also. Then the model might not overfit. Uh, Again, another okay. If you let's say you have one person asking the question, okay, to try to figure out whether the other person will play or not. Okay. The judgment of the person asking that question, okay, might be different. But let's say you ask like two or three more people are asking different questions to the same person. Okay. In that way, you sort of again get majority. If two people say that okay, this guy is going to play, one is saying this guy is not going to play, then you say the probability of that guy going to play is more because two people said yes based on their set of questions. So what I'm trying to say here is when you combine different models, or in this case decision trees, better will be the performance of your like resulting downstream models. And that is where like sort of random forest comes into the picture. Okay, you can see this picture. Let's say this is a basket of fruits. Okay, I want to check whether there is apple here or banana here. Instead of one person asking multiple questions, I say that okay, let me ask different people to look at this fruit basket. I won't like one might be colorblind and he cannot see red and he can say it's banana or something. It can be like that. So what you do is ask multiple people to look at the same fruit basket and let them choose whether there is a banana there or apple there or so. Here two people said apple, one said banana. I'm going with apple because two people said it's apple. Okay. And this is what essentially a random forest is. Collection of trees, you have a forest. Okay. That's what it means. This is the decision tree and random forest. Hyperparameters here can be the number of trees, the number of features to select, uh, how many questions you can ask. These are different hyperparameters that you can do. Again, validation, you would use the k-fold cross validation and check the performance of your model. That's it about decision trees and random forest. Any questions? Any doubts? Any questions? I hope you all understood. I think I went a bit fast, but if you have any doubts, you can ask. Okay.
No,
Okay
sir.
then.
No
Okay.
doubt, sir.
Okay. Okay then. If there are no doubts, we can. I mean, tomorrow I'll be starting with the tutorial section where we'll be writing Python code and see how these models work. And if there are no questions, we can end this session for now. Thanks. Thank you for joining.
Thank you, sir.
Thank you, sir.